company innovates, and the high-state technology we have developed in the last year. I will drive you to my speech, starting with some introduction about the company, the key figures. Then I will deep dive in our new electrolyte, which is SO2 based, show how it works. I will also show some real performance data we have achieved on 21700 cell performance, and continue with the conclusion, including our technology roadmap. I founded the company in 2018 with an expert battery team, and today we are about 80 people on 3 different locations. We have our headquarters, which is located in Basel, Switzerland, our Research and Development Innovation Center in Bruxelles. It's close to the Frankfurt airport, and we have also a China office in Beijing. The company was founded with the support of an investor and a commitment capital of about 100 million, including the commissioning and the installation of a lab line, which is today fully operational. And we produce on this lab line some cells for our customer qualification, but also to support our research and development activities. Our main differentiator is an inorganic, non-flammable, high-voltage stable electrolyte. I will detail later. We name it high-state, and our technology is also fully protected. We have more than 325 granted patents, and 70 more which are on the way to be granted. When I started working on batteries for about 2 decades now, the main applications for lithium-ion was consumer electronics. Thanks to the coming electrification, this is now completely different. But still a lot of barriers needs to be overcome. For example, the cost needs to be reduced in order to reach parity, at least with conventional cars. The energy density needs also to be increased in order to give more flexibility to our customers and reach longer driving distance. This is a very important item, the extension of the temperature windows, which was especially a hot topic during the winter time in Europe, where customers noticed that even at 10 degrees C, driving an electric car has some limitations. Fast charging is something which is required, addressed on mechanical design, but here also some chemical potential is available. And safety is also something which needs to be improved, and not by doing a step back, for example, by introducing LFP material, but the safety needs also to be improved with high nickel containing cathode materials. And the last but not the least, also important, we have to extend the recyclability to all compounds, including electrolytes, in order to be able to introduce lithium-ion batteries into the circular economy. That's an important slide. It was during our development phase, we took special attention in order to be fast in the market and also price competitive, to be as close as possible from conventional lithium-ion cells. So that means we developed our technology, having access to all the supply chain which is currently available. We are using same active material, same current collector, also same housing, and our cells can be produced with the same equipment. We are compatible with a silicon-based anode, and additionally, our electrolyte enables us to go to a higher potential. And we are also compatible with anode-free concept. How work our electrolyte? I started working on inorganic electrolytes for about 2 decades now, made my PhD on this topic, and this was a formulation which was used for our first generation. It was lithium tetrachloroaluminate formed by using lithium chloride and aluminum chloride, and SO2 was used as a solvent. Fantastic properties, like for example, high conductivity. More than 100 millisiemens could be reached, per centimeter could be reached, and extended temperature potential. For example, also at lower temperature, it was working quite well. No flash point, it was fully non-flammable. But one drawback, corrosivity. This electrolyte was highly corrosive, and we had to select specially the compounds in order to build a stable battery. But this was not the only limitation. We observed during investigations that the electrolyte had an issue with higher voltage. So what you can see here is a cyclic voltammetry we have done, and above 4.1 volts we observed oxidation of the electrolyte. By investigating deeper, we find out that the chloride was oxidized, forming chlorine reacting with the solvent, producing sulfur chloride, which was then also reacting with other compounds in the system. So the limitation could not be overcome chemically, so we had to use cathode material which had a working potential below the oxidation. That means we could pair this electrolyte with the LFP graphite system and reach a high stable system. More than 5,000 cycles could be validated, and it was produced at mass scale for ESS application. What we have done in 2018 at Inolit is we did a large screening to solve exactly this issue of oxidation stability. And we tried to find a way how to stabilize the unstable chloride bonding. More than 50 different salts were investigated, also a lot of different recipes on the electrolyte side. And what you can see here is a corrosion test we have done in order to discard the different formulations. And in red, you see our first generation. A current is applied on an aluminum current collector, and potential reply is analyzed. And so you see that with the first generation, below 4 volts, a constant potential without changing, meaning that oxidation of electrolyte happens. And with our new generation of electrolyte, we have seen that even by increasing stepwise, the current potential was also increased but stays stable until we reach the limit of the testing device, which was 6 volts. This was our first important milestone in the development. And after showing the high voltage stability, we were also investigating the low temperature, the low potential stability, which was also very good. So we could cycle graphite and lithium in a very stable way. We also measured the conductivity, which was a bit lower than what we measured in our first generation, but still good in comparison to organic electrolyte. This is also directly related to the low temperature limit, which was defined as being at -60. So I will show later some data on a real cell. No flash point, because the compounds of the electrolyte are all fully non-flammable. And we could also show stability with all commercially available materials. This is a sheet to show charging and discharging curves to explain what we have done with our first product. It's NMC 622. So you see the limitation is normally for organic electrolyte at 4.2 volts. And with our Inolit electrolyte, we are able to go to 4.6 volts and therefore have access to more specific capacity. We just show before a presentation showing that the fourth phase in NMC is not stable. This was also our understanding before we made our investigations. And what happened in organic electrolyte is well described in the literature. You have a reaction at elevated potential. Oxygen is released, react with the electrolyte, forms HF, which is even more aggressive, dissolves the current collector and reacts also with the NMC itself, and the system gets completely unstable. In our case, we observe that we do not have this oxygen which is released. The NMC stays stable and can be cycled for more over 1,000 times, even if we go at 4.6 volts. In general, we have also no formation of HF, even if we have water inside the system. And at high potential, the system stays stable. In this section, I will show how we address the high energy density, also our performance at low temperature, and show some real cycling data which were achieved on cycling at between 2.5 and 4.6 volt. So all this testing were done with cell produced on our lab line with a 21700 format. So you see here, it's a discharge curve with C/5, and the cell was before fully charged at 4.6 volt. So the discharge is starting higher than 4.5 volt, and as we are pairing our cathode material with graphite, we have a higher mean discharge voltage. That additionally to the higher specific capacity we are reaching means in total our cells with NMC 811 and graphite are able to reach 5.3 ampere hour and contains 20 watt hour energy. There's something wrong with the graph. So on this graph, I wanted to show that we have different I will explain it. So it was different charging cutoff voltage which were investigated starting from 4.2, where normally organic electrolyte needs to stop and see the difference in the capacity which is achieved. So 4.2, 4.4, and at 4.6 volt we are able to reach 5.6 ampere hour with a C rate of C/10 and energy density at the end of 310 watt hour per kg. This is our low temperature performance. Due to the high conductivity of more than 40 millisiemens per centimeter, we are able, even at -35, to reach a residual discharge capacity of more than 80%. The same for charging, -20. So we are able, without reaching lithium plating, to charge our cells at 85% at -10. At C/5, which is also a very good low temperature performance. And the last performance data is about cycling. So the question was always, is it possible to cycle NMC 811 or NMC 622 at this elevated potential without having a fast capacity drop? Yes, it is. It's working. So this cell were cycled with C/2 and C. So it was a higher C rate design, reaching 300 watt hour per kg. With C/3 cycling, we are able to reach even more cycle. Here the prediction is to be able to reach 800, maybe 900 cycle, which will be enough for EV application. That is our UN certification. Our current product specification And I will finally come to the conclusion. We'll show our roadmap. So I showed the bottom line where I was concentrated today. NMC 811 graphite. We are working on some mechanical optimization in order to reach 220 watt-hour per kg. We have in our pipeline high nickel containing cathode material which will be combined with silicon graphite anode in order to reach even higher energy densities. We have also a lithium metal concept which was developed in the lab. It was a 7 ampere hour, 21,700 cell, reaching more than 400 watt-hour per kg. Our electrolyte is also working with sodium, and I want to concentrate on the top line. You see LNMO, lithium manganese rich, and LFMP are materials of choice for us. We also observe that manganese is not dissolved in our electrolyte, and combining this material with high voltage stable electrolyte would be, according to us, the next generation of electric vehicle batteries. So I will finally come to the conclusion. Thanks to the high voltage stability, we are able to save costs per kilowatt hour. For the same reason, we are able also to save some material and reach higher energy density, 300 watt-hour per kg is our standard energy density. The high conductivity of the electrolyte gives us an extended temperature window, especially at extreme temperature at -40, our system is working. High C-rate capable, and additionally we have also a huge advantage in terms of safety due to the non-flammability. So -40 to -50 less energy is released during thermal runaway, and our electrolyte is fully recyclable, giving one piece more in the puzzle of reaching the integration of batteries into the circular economy. Thank you.
好，谢谢。那由于时间的关系，我们还是提两个问题啊，给同学啊。
不好意思啊，我是蔡生照啊，这个近水楼台了。我先问一个问题，我刚才特别注意您讲的这个电池啊，300瓦时还是用 NMC 和石墨做的，然后还能够零下40度，这个还能1100次循环。我看到你这个数据啊，如果是这个数据的话，在国内，在咱们这个行业里面也是非常牛的一种存在啊。我想知道啊，如果这种电池的话，这么优秀，在我们的国内的话，我们从来没有知道有你们这么好的技术，这是第一个啊。第二一个就是我想知道，您是怎么实现的？然后，您来到这个中国啊，您是希望和中国的企业或者这个产业界要怎样的合作？还有一个我想知道，你这个电池的话，是量产的还是实验室产品？然后以及你在中国的话，这个是什么样的一个售价？谢谢。是不是太多了问题？还是需要翻译一下？
Sorry. Can maybe someone translate?
I try to translate that. He mentioned your presentation has shown very excellent battery performance. What's your future? It is plan you set up a joint venture plant in China, or how to expand your future business?
Thank you for your question. Our business model is based on licensing, so we are interested in finding partners in China to license our technology, and of course also doing a joint venture agreement with a player from the lithium-ion market.
你的问题太多了，下面再交流，好吧？好，谢谢。还有谁可以提一个问题？最好直接用英文啊。
Thank Thank you for your report, Dr. Lo. You show the battery is a good low temperature performance. I just want to ask the battery can with the electrolyte can charging at a low temperature, example at negative 35 degree. And if yes, the performance, how the performance, and if not, you have some ways to release this battery charging at a low temperature. Thank you.
We have measured conductivity of our electrolyte, and even at -40 we are able to reach around 20 millisiemens per centimeter, and this gives very good residual conductivity. So that means at -40 degrees C we are able to discharge even with a not optimized mechanical design more than 80%, and at -20 degrees C our cells can be charged without entering into lithium plating. I think it's charging at low temperature is always challenging for the lithium plating, and this needs to be fully avoided.
Thank you.
Okay. Thank you again.